Hi, I'm Raymond Peck. Welcome to ML 103, How to Avoid Common Machine Learning Potholes and Landmines. In this talk, I will be making some forward-looking statements. These forward-looking statements are subject to change. Please do not make any purchase decision based on these forward-looking statements, but only on the features that are currently in our products. Thanks. So this is the third of a set of 3 sessions which are intended to introduce machine learning to people who either have no experience with it or are self-taught beginners. Often when people self-teach machine learning, they can get some good results pretty quickly but miss some important things along the way, particularly problems that can come up during projects that we can take care of if we're looking out for them. But if we're not looking out for them, can kind of derail things. And I'm calling those potholes and landmines. In this session, we're going to see problems that can occur in a lot of different stages of the machine learning process. And we'll see, how to begin to address those. The important thing here is that you're aware of them as we go along through the machine learning project workflow so that you can look out for these problems and take care of them. So all of these gold areas are steps that we're going to see issues with that we need to keep in mind as we're doing our projects. The first one of them is down at the bottom, specifying the problem. Now, in the prior 2 sessions, we talked a little bit about how understanding how we're going to quantify what it means to have a good result is really important, and matching up the metric that we use to measure our models to our business aim is critical. It's no more critical than in binary classification, and I want to give you a little bit of background to understand how things work with binary classification. So models in binary classification models return a probability that something is true. So a probability that a transaction is fraud, or a probability that a customer will churn, or that somebody has a disease, something like that. And we have to choose a decision boundary where we're going to say if the probability is above this number, if it's above 0.5, if it's above 0.6, we're going to predict true, and if it's below that number, we're going to predict false. That's what this decision boundary is. Now, what that means is that we can change this decision boundary to have different trade-offs between false negatives, false positives, true negatives, and true positives. If you take a look at this, this diagram, we call this the confusion matrix. It's very common in machine learning when dealing with binary classification problems. And it lets us see the count of predictions that are actually negative and were predicted negative. Those are called true negatives. Ones that are false positives, which, in these days of COVID, we probably understand that. You have a positive result from your prediction, but the actual value is negative, and so on. And so if we look at this, there are 4 different quadrants here, and there are actually 4 different stripes. We have all the actual negatives, all the actual positives, all the predicted positives, all the predicted negatives. Now, the metric that we use lets us tune the model to answer questions about any of these areas. So if we're more interested in false positives, for example, that can help us ask the question, why did this model think the valid transaction was fraud? Right? So if a valid transaction was predicted fraud, we care about the false positives, for example. So the metric that we use lets us balance our results across those areas. So for example, if we're interested in the fraction of all of our predictions, whether they're true or false predictions, then we care about accuracy, right? If we care about the correctness of positive predictions, for example, if we predict fraud, how often is that prediction correct? Only for the positive case, that's precision. What fraction of the minority cases, what fraction of fraud, for example, or churn do we detect? That's called recall. So it's important to take a look at the definitions of these and make sure that the one that we're using matches with our business purpose. Now, the next step is data prep, and a lot of time is spent in data prep. We talked about having to make sure that our data that we're going to train our models on is representative of data that we'll see in the future. We want to make sure that it's clean, it doesn't have a lot of errors in it, but there's some other issues we have to watch out for. So let's take a look at this example. And here, this is some data on diamonds. And we have an issue here where we have cut, color, and clarity all mixed together into one column. Before we do machine learning, we'll want to pull these three apart into three different columns. We have a column that's a currency, and it happens that all of our rows use the same currency, so this is not a useful column. We'll want to throw that out. We have this missing value here, and we should look at our missing values and decide whether or not it's actually meaningful to have missing values in a certain column. The example that I like to give is if we're trying to predict a disease for a patient and our data has test results in it, it can be meaningful that a doctor did not order a certain test because the doctor is sort of injecting some of their knowledge into the data set. So if the doctor didn't order the test, we probably want a flag on that column, on that feature that says, you know, this test result was missing because it wasn't ordered. So other things that we have to look out for are analytic types. So what this means is that certain columns could be interpreted a couple different ways. If we have a small numeric value, that could be something that is actually numeric. It has a count kind of meaning or something like that. Or it could be a category, right? It could be a number which represents the country of origin of some transaction, for example. And that's encoded as a number from 1 to 200 and however many countries there are today. And, you know, if we have something that's a category, we probably do not want to treat it as a numeric value because there's no ordering to it and so on. Similarly, if we have strings of text, those could be a category, again, like the name of a country, or they could be some natural language, like some text coming from a chat from a user. How we're going to analyze the data for those two different cases is different. So our software will always do its best to try to figure out which of these cases there are, but there are certain cases that it just simply can't distinguish. If it sees a column of 1 through 5, it doesn't know that those are numeric versus a category. So it's important to check these. Next, our software will point out outlier values, and we want to take a look at those and make sure that they don't indicate problems with our data that we have to deal with, or cases that we maybe don't want to cover. And I'll show you an example of that in a minute when we look at a regression problem. Another issue is class imbalance. So if we have a classification problem, and we have something like a fraud data set, the number of cases of fraud that we have in the data set is going to be very, very small compared to the number of cases of non-fraud, we would hope. And so our software will help us to manage that, but we might need to pay some attention to it and make sure that the class imbalance is handled correctly. So let's talk a little bit about feature selection and issues that can come up. So we talked a little bit about this before. And the fact that we want to remove non-noisy or noisy, non-predictive columns, like the one that we see on the right, where there's no relationship between the X and the Y. On the left, we see that there's a relationship here with a little bit of noise in it, but there's clearly a pattern going on. So we want to remove noisy columns. We want to remove correlated features. If we have features that are correlated with each other, for example, we have height in inches and height in centimeters, we'll want to remove the extraneous ones because having them in the model doesn't cause a problem with the predictions, but it makes it difficult to interpret the model. If we have two different height measurements for a patient, for example, and we're trying to understand what the model is doing, it could use all of height in inches and none of height in centimeters, or it could use the reverse, or it could use a balance between the two, and it's random. So it really helps to interpret models if we remove uncorrelated features. There's something that comes up that you might hear about called the curse of dimensionality. And basically what it means is that the more features that we have, the more dimensions that we have, the harder it is to fit the model to the data. And so we want to make sure that we have predictive features, we don't have extra features that just add noise, and we want to make sure that the number of rows that we have is much larger than the number of columns. One caveat is that interactions between features can sometimes make it look like a certain feature when you look at it by itself is not very useful, but if it's combined with another feature, then it is useful. Example that I like is acidity and wine. The wine type changes the meaning of acidity if you're trying to predict quality. Lower acidity is associated with higher quality white wines, and higher acidity is associated with higher quality red wines. So you might throw out acidity thinking it doesn't mean anything, but it interacts with the type of wine. We also have to be careful in feature engineering that we're not adding correlations between our new features and our existing ones. So we have basically the same issue with correlated features. We want to be careful that we don't hurt our prediction. Now, something that comes up that is more subtle and can't always be handled by our software is called leakage. This is something that I want to make everybody aware of because it's a very common issue in machine learning projects, and it's very hard to detect until you put the model into production. What leakage is really is that there's some information known about either the target variable that we're trying to predict or something else that shouldn't be known and can't be known when we're making a prediction. And there are three really different categories of leakage. One is a trivial example. So if I have a data set and I have the target variable I'm trying to predict, and I have a feature that is really a copy of the target variable, and it's not something that I'll know at the time that I want to make my prediction, that's a trivial leakage. A time leakage is if some data is introduced at a certain time and it won't be known at prediction time. For example, if I have an aggregation, which is the total value that the customer has spent, and that includes spending that they made after we need the prediction time, then we're kind of leaking data into the future. Our model, when we train it, knows something about the future. Similarly, if we have groups of rows in our data, for example, if we have a number of rows for a given patient, we need to make sure that when we do data splitting, that we keep those rows together. So the real problem here, and the reason I'm emphasizing it so much, is that the problem won't show up in development. Even if we do a test train split for our data, we hold back some data, and then we use that to evaluate how well our model is doing, the leakage will occur in the holdout data as well. And so it'll look like everything is going fine, but in fact, we have a model that won't work well in production. So for most of these cases, Alteryx machine learning and feature tools on the open source side will help you with things like time-based. But if you do your own aggregations and you do your own data splitting, you have to be very, very careful not to introduce leakage. Now, I'm going to talk a little bit about overfitting. And we saw this example last time of making our model more and more complex to try to have the green line, which is our model, match the red line. And we got to this point where the model was too complex for the data. Well, how do we handle this? The first thing is that the way that we'll understand that this is occurring is that the performance on our holdout data is not as good as the performance on our training data. So if we look at our metrics, our training metrics will look great, our holdout metrics will look terrible. That's a big red flag. But there are a couple different ways that we can control this. The first is just throwing more data at the problem. So if you make the amount of data more than the complexity level of your model can handle, then it will smooth out the model, basically. So we see this example here where I've just thrown some, 10 times as many points at the model, and it fits the red line a lot better. Other ways that we deal with this are doing test train split, holdout data, right? Very, very important. And cross-validation, which is a little more complex version of doing holdout data. So one thing I'll note is the fewer the rows we have, the more critical overfitting is. So you have to be extra careful when you have a small number of rows of data. I'm talking, less than 1,000 rows, depending on how many columns you have. So talked a little bit about data splitting. Data splitting is really important because each stage of our process as we're going through the workflow is getting matched to the data that we're using for that section. And whether that's feature selection, feature engineering, model training, model selection, in an ideal world, each one of those steps should have its own split of the data. And that way, it's not fitting, we don't have successive stages of this process fitting to the data. So here's some important guidelines I'm going to go through really, really quickly. If we have grouped rows, like our case where we had multiple rows per patient, we have to keep those together when we split. So we don't want to have some records for a patient in the training data, train the model on it, and then use information from that same patient, to evaluate the models with our holdout data. If there's time dependence between rows, you have to split across time. If the data is independent, all the rows are independent, then it's the very easy case. We call this data IID. And it means that all the rows are independent and equally distributed, and we can randomly split the data. So when we do model tuning and we're turning the knobs of our model, like we saw earlier, part of the tuning knobs are control of the complexity of the model. And so we want to be careful that when we're tuning those knobs, that we're evaluating not based on the training data, we're evaluating the models based on the holdout data. Right? Fortunately, the tools nowadays like EvalML and Alteryx machine learning will help us with that. Now, back to the topic, kind of at the end of the process, back to the topic of correlations. When we're looking at feature explanations, prediction explanations, there are a lot of tools that we have, particularly in Alteryx machine learning, to help you understand what the model is doing. We always have to be careful when if we leave in features that are correlated with each other, that those features will act together as a group when we're looking at these explanations. Finally, when we put a model into production, we're not done. What happens almost all the time is that things will drift over time. You can think of an example again of fraud, and part of our model might be looking at transaction sizes. Well, over time we have inflation, right? And transaction sizes go up. In addition, people earn more money over their lifetime, right? And so if you have models that are doing a prediction for something that changes over time, you will have to monitor that, make sure that your model keeps predicting in the way that you expect, and also monitor the data. Make sure that the data that you have today when you train your model is very similar to the data that you have in a year when you're trying to use that model still to make predictions. So just wrapping things up, there are a lot of places we can make missteps, but as long as we're looking out for them, we can avoid them. It's very easy to throw some of this machine learning software at a problem, not pay attention to any of this, have something that looks like it's good, but it's not as good as it could be, or there could be kind of problems lurking underneath. So it's good to understand all of these concepts and how the software that you're using, like feature tools, EvalML, and Alteryx machine learning, are helping you to manage these. And especially watch out for leakage, because if you're depending on the tools to do your data splitting and to do your balancing for you, you're probably in good shape. If you're doing your own aggregations and your own data splitting, be extra careful. So I guess that's it for this session. Keep your eyes open, and I'm sure you'll have a great, successful project. So please join us now for a brief survey. And thanks so much for watching. Bye.